Hi, and good afternoon. My name is Freddie Drennan, and I'm a data scientist with Digital First Media. I do a lot of linear programming at work, and I always love these types of problems. Classic problem is called the transportation problem, where you have a certain group of items that you want to get from, you know, s- location A to location B. Most of the problems that you see in class are pretty simple. This is going to be slightly more advanced, something that you could kind of expand on. Um, let's just get at it. In this particular case, we're going to make a graph first, and we're going to build that math problem off of this graph. So we're going to say we have items that we want to take from locations A and B. So these might be like distribution centers. These might be people that you're picking up to take somewhere. Maybe you're like a ride share. I don't know. So these are our two initial locations. Each of these locations, okay. The next thing that we want to do is define our ending points. So it might be like locations 1, 2, and 3. But there's going to be paths along the way. You know, um, Different costs associated with different routes. So in this particular case, we're going to say we've got a, a turning point at C, which we call nodes here. So we have nodes at C, D, and E, F, G, and if you can't tell, I've already kind of done it, and I'm just writing it over here, G and H. All right. So these might be streets, and we can kind of interpret these here in just a second. All right. So we have location A, and there's some sort of decision made at C, and there's some sort of change made at D and E. Um, Same thing here with B. So B, you have two options to go left or right here. F, you could actually, kind of come into this location over here, and then we've got, H here, which gives you two options to these two locations. So these are our pathways. So maybe this is your um, distribution center in in Houston, and then you drive to San Francisco here, and then in San Francisco, either that item goes up to Washington, or it goes across the ocean to China. Well, they're trying to get to the same location, so maybe that doesn't necessarily make sense. Um, okay, here we go. This is Beijing. Um, it's flown to Taiwan, and then from Taiwan, either it can be shipped by boat or it can be, flown over. So if it's flown over, it goes into Los Angeles. If it's shipped, it shows up in Washington, and then there's the final location somewhere in like Oregon. So let's just assign some costs here. So from A to C, we're going to give it a cost of just 1. C to D2, D to the final destination, we're going to give it 3. And then we're going to give C to E, actually let's not give that 3, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So these are our costs that we're giving these things, these different pathways. Um, So the cost of these um, pathways would probably be determined in advance. So maybe you do some sort of cash flow model. You determine the distance between these two different locations. If it's a transportation company, maybe you go in and you add up bus maintenance plus or bus depreciation plus like paying the drivers plus anything else you can possibly think of for each of these different nodes. And then you can build a model and see what the best path to take your supplies from one location to the other is. So we're going to say at location A that we have 500 units of things. And then at location B, we have 600 units of things. And location 1 requires 200, location 2 requires 200, location 3 requires 200. And so the question is, how do we find the minimum cost? Well, the first thing that we would want to do is we would want to decide what we want to minimize, and that is the cost per unit of transporting these items. So right here, if we have 10 units go through this pathway, it's going to cost us $10. And so we've got $10 going through here. There's a pathway here, a pathway here. So we've had 10 units that are coming this way. Well, the shortest path would probably be to go this direction because it's going to cost us 20 units or $20 instead of $30 over here. Now, this is a pretty simple problem. So you're going to think, well, so this location here needs 200 units. So we're going to take 200 units over here, and it's going to be 200 times 1 times it'd be 200 plus 400 plus 800. And that would be the total cost of shipping these through, because we've got 200 that's going this way, 200 that's going this way, and the 200 that's going this way. Now, this is kind of a toy problem. What if, for example, this cost was variable each day and ended up, costing 6? Well, now maybe both of these pathways are now equal, but then, maybe the next day this costs 60. Maybe something happened here, and there's like a storm or something comes in and blows up. Storm blowing up, just like takes out a warehouse or something, or takes out a road, right? And you got to wait. You'd have to sit around. Maybe there's some just waiting costs for this pathway. I don't know, but you could model all those things through some sort of diagram like this. So what we're going to do is we're going to give all of our variables. Give everything a variable here. So this is x3, x4, x5, ... And so what we want to do is we want to minimize 1x1, 2x2, plus 3x3, plus 4x4, plus 5x5, plus 6x6, plus 7x7, plus 8x8, plus 9x9, plus 10x10, plus 11, and plus 12. All right. And so the question is, okay, well, how do we write the math for this, right? Well, we can use linear programming, and what we've done is we've written an objective function here. So we want to minimize this function here based on constraints that we're going to build out. So we know that location 1 requires 200 units. And so we know that x4 and x5 are going to require, we're going to have to get 200 units between these two different pathways here. So what we can say is that 1x4 plus 1x5 is equal to 200. Well, that's great. What about node D here? Well, if something is in node 4, then it's going to require coming through. Well, I'm saying node 4. This is pathway cost of 4, x4. Pathway x1 is going to require that amount as well. So what we can say here is that 1x4 minus 1x3 has to be equal to 0. So if something comes up through x2, it has to go through x4. So if, say, this is equal to 200, right? So x3 is equal to 200, then x4 is going to be required to equal 200. And so, and then this would be required to equal 200. And then we've satisfied, you know, that constraint over here, filling this up with 200. What if, well, let's not get there. All right. So now passing this, you know, going this pathway here. So if something is in x1, it can either go to x2 or x3. So whatever is coming through x1, x2 and x3 have to sum to it. So we can say 1x2 plus 1x3 minus x1, 1x1 is equal to 0. So anything that comes through this way, you know, the units have to sum up over here. All right. So now let's go back this other direction. Well, if something comes through x3 or x6, x5 has to equal that. So we can say 1x5 minus 3 minus x3 minus x6. So this is minus x3 minus x6 has to be equal to 0. All right, let's think about this now. So we know that x11 has to equal 200 because we require 200 units over here. So we can say x11, 1x11 is equal to 200. All right, and so what we're doing here is we're setting up, you know, what these units have to be, and then these are the costs up here. So for example, we know that we're going to spend 200 times, well, either, you know, 200 times 4 or 200 times 5, but everything's going to come through here. Let's just keep going. All right, so 11, well, this is 1x11 equal 200 right there. All right, so coming down this pathway, and then, oh, let's do this, and then x12, 1x12 has to equal to 200. All right, so we've knocked these paths out. What's the next one? So now we also know that whatever's coming through x9 and x10, x11 and x12 have to sum to that. So 1x11 plus 1x12 minus 1x10 minus 1x9 is equal to 0. So whatever units are coming through here, you know, say we have 50 here and 50 here, you could have 100 here, or you could have 100 here, or you could have 75 here or 25 here. But whatever's coming through this funnel, on the other side of that funnel, your units have to sum to that. All right, so we've knocked out this location and this location. So now we have this pathway going backwards. So we've got 1x9 minus 7x9 is equal to 0. So 1x9 minus 1x7 is equal to 0. All right. We've done that. And then we know we've got that taken care of. And then going down this pathway, x10 minus x8 has to be equal to 0. x10 minus x8. So x10 minus x8 is equal to 0. And that's it. So we've written out this series of equations that describe all of the relationships in this graph here. And if we go to R, I've already mapped it out for you here. So for example, this is that matrix that we just wrote of all, so wherever I left out a coefficient, it's implied that it's a 0. And so what's going to happen here is that this is what is our objective function. This is our coefficient matrix. Okay. In R, this is the right-hand side coefficient, and then these are the directions. Now, we said that we didn't quite finish this problem, actually. So there's one thing left. We also need to specify the amount of things at the original locations. So here at x1, x1 has to be less than or equal to 500 units because we don't have more than 500 units there. And then x7 and 8 have to be less than or equal to 600. So x7 plus x8 have to be less than or equal to 600. All right. So that right-hand side coefficient, those right-hand side coefficients are right here, just in a slightly different order. So 500, 600. So x1 has to be less than or equal to 500, right? x7 and x8 have to be less than or equal to 600 right here. Ooh, that is really awful to read. Sorry. And so you just basically print out that matrix of relationships, and then I'm going to rewrite these coefficients here. 1, 2, 3, 4, 5, 6. All right. These are all of our zeros, and then these are the 200s for the destination unit requirements. Yeah. So this is it, and I can go ahead and run it, and we get some results here. And let's interpret these results. All right, so x1 has to be equal to 200. And actually, let's we can clean up a little bit of this. Maybe not. I don't know. Let's just make a new one. So A, do C, D, E, 1. And B, F, G, H, 2, 3. And our original coefficients were as follows, or the costs. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right, so x1 has to be equal to 200. So 200 is going to come through x1. And remember, we had 200 here, 200 here, and then 200 here as a requirement. We've got 600 here and 500 here. All right, so 200 leaves x1, goes to x2, 200, which makes sense, right? x3 gets nothing. Nothing comes through x3. x4 gets 200, and that's that pathway. And then x4, x5, x6, x7. So 400 leaves x7, which makes sense, right? And then 0 goes through x6. Well, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. 0 goes through x6, 0 goes through 8, yep. 9, 10, 400 goes through, hold on, this is 9, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. 400 goes through 9, 400 here to 9, 9, 10, 11, 12. So 200 goes through 11 and 200 goes through 12. What happens, say, if we increase the cost of A right here at this initial node, like really high, right? What if it was really, really expensive to leave and go right there on that pathway? Well, we can simulate that. So here we see that nothing leaves x0, nothing goes through x2, nothing goes through x3, x4, and then let's look at x5. Wait, 1, 2, 3, 4, 5. Okay, so 200 is coming through here. Oop. 200 is coming through x5, x6, 200 came through x6, right? And then 600 left from x7. x8, x9, 400 went through x9. So what happened here is that we said that original cost from that distribution center was really expensive. So let's see here. C, I'm pretty messy, guys. E, 1, 2, 3, 4, B, F, G, H, 2, 3, and this was one pathway here, pathway, 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 pathway. So what happened is, and I think that, I was wrong. I said 500 so this is where I screwed up. I said 500 here and then 600 here. So we'll say 600 is here, 500 is here. All right, and so what happened is, we said this is 11 now. 11, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So given that this was such a costly path, 200 came through this pathway, and then 400 left here, and then 200 went here, and 200 went here. So that's how that solution came about. But let's put it back at those coefficients that I'd said a second ago, right? So there's only 500 from the original location. There's 500 from down here, 600 in demand, and then there's 600 up here now. 600, 500, right? So now we see that 100, 100, so x1, 100, x2, 100, 100, and then x1, 2, 3, 4, 5, and then 100 came through here, 100, 500, 200, 400, 200, 200. So because there was limited supply over here, we had to put 100 from this very costly pathway. What are some other things we could think about? I don't know. I'm going to call that good. But looking at LP solve, just real quick, our solution is here. And so what you would do, if you wanted to look at the total cost for this, for the solution to this LP, it's as easy as this times your objective direction, objective function, or you could just do this. Get your solution here. So I hope that was useful. It was very fast. I'm going to put this on GitHub so you can take it and then watch through the video, and you can sit over here and play around with it. So that's all. Thanks.